In this video, we want to take a look at how we could find the surface area of our volumes of rotation or our solids of rotation. So what if we had a function and we rotated it about the x-axis? To be. Then how could we find for this volume or this solid just the outside surface area, just the area that could get painted of this vase-like shape? Well, using integrals, we always have this start of let's split up our interval and look at one specific spot, an xi star, and say, what if I'm looking at trying to find the surface area at that little spot around xi star? Well, zooming in on that little piece, that creates the bottom half of a cone type shape of having a cone formed. And we are looking at the bottom chunk of that cone. So since we're looking at the bottom chunk of a cone, what's useful to know is that the surface area of a cone in general is pi times r times L, where L is the length of the side. In this case, I want to have you recall in our last videos talking about arc length, L ultimately, when we take all of these little cone-like pieces and add them up, L will become the arc length of the volume, the solid. So using this idea of the cone being pi r L, we want to look at the full cone, see if we can find the surface area of just the small part of cone. So the part of cone we want to know has the length L and a big radius R1 and a smaller radius R2. And the rest of cone, this is the part that's getting cut off, we're going to call that side length L2. So the surface area of the truncated cone, just that bottom bit of cone that I'll highlight, just the surface area of this part going all the way around is the surface area of the whole cone, which is pi times R1 times L plus L2, L plus L2 being the whole length of the side of the cone, minus the little cone that we're cutting off. So whole cone minus little cone. And this radius is the R2. There we go. Sorry, an L2. We don't have an L1 defined. Now, Multiplying this out, we get pi r1l plus pi r1l2 minus pi r2l2. And refactoring, get pi r1l plus pi l2 r1 minus r2. Now, we would like to be able to rewrite this in some nicer ways. In particular, we'd like to be able to rewrite this pi L2 R1 minus R2 in a different way. Specifically this part. So using the idea of similar triangles, we actually know that the whole big triangle piece, which is R2 over the whole big triangle would be R1 over L plus L2 is equal to the little triangle formed by the cone. Right. So R2 over L2. Multiplying this out, we get L2 R1 is equal to R2L plus R2L2. Subtracting R2L2 over L2 R1 minus R2 is equal to R2L. So by similar triangles, we actually get this part underlined is the same as R2 times L. So this equals pi R1L, keeping that first part the same, plus pi R2L. Which we can see is the same as pi R1 plus R2L. We still would really, really like it if we didn't have two triangles that we're worried about, or two radiuses that we're worried about. So, trying to get rid of these two radiuses, we have this big radius and little radius. There is some third radius inside of there that's the average of these two radii. So R, some radius that we want, is R1 plus R2 over 2. Or 2R is equal to R1 plus R2. Meaning, from these similar triangles and from that average, we get 2 pi R for that radius in between L as the surface area of the truncated cone. That was the whole aim. What that formula gives us is if I can identify what a radius is in this picture and what that length is, already mentioned previously, we can find our surface area formula. Well, R is our distance from our x-axis up to our function. It's that average of the two radiuses that we are looking at. So r is the function at xi star. And L is the arc length in terms of what we currently have in our picture. That is the square root of 1 plus the derivative at xi star, delta x, the derivative squared. There we go. So the surface area is equal to the limit of the sum n of 2 pi fxi star square root 1 plus f prime xi star squared delta x. This now turns into an integral. So if I have a function greater than 0 with the derivative continuous, the surface area of the surface obtained by rotating y equals f of x about the x-axis is the integral from a to b of 2 pi f of x square root 1 plus derivative of x squared dx. This is rotating about the x-axis. If we wanted to go about the y-axis, we would do in terms of y. So s equals the integral from c to d of 2 pi g of y square root 1 plus g of y squared dy. So these are our formulas to be able to find the surface area from a surface being rotated, or one of our solids of revolution. We will work with how to use those in the next examples.